Good. So if that is good, then let me go ahead and switch topics to the next topic, which I wanted to talk about in this class. And this topic is the topic of writing semantics and writing an interpreter. So writing an interpreter. Okay. So let's see. Before I do that, are there any questions that I should talk about? Is the skipping present in lecture recordings? Not that I can see usually. Okay. All right. Yeah, so next week, let me do it from my house and we'll see how that works out. All right. Question? No. Okay. All right. Thank you. Okay, so now I'm going to switch gears and I'm going to talk about writing an interpreter. And we're going to talk about writing an interpreter for a simple arithmetic language. Simple arithmetic expressions. Okay, so I'm interested in writing an interpreter for arithmetic expressions. So what are arithmetic expressions? So arithmetic expressions are expressions that are generated by this grammar, the grammar over here. Okay, so these are arithmetic expressions. You've seen them. I mean, they have made their appearance in the class, and you had some questions in the assignment that's due tomorrow, where you saw some arithmetic expressions in the language. So I'm going to start with these arithmetic expressions, and I'm going to talk about how to interpret these arithmetic expressions. All right, and that's going to be the simplest. So that's going to be the simplest. And then I'm going to build features on top of arithmetic. I'm going to build conditional expressions. I'm going to build up let bindings or assignments of a form. I'm going to add function calls. I'm going to add recursive functions. I'm going to add ability to change the value of a variable or mutation. So we're going to start to build up a language with this as the base. All right. So to do that, we need to first start to figure out, like, how do we interpret arithmetic expressions? What does it mean to interpret something? And last but not least, how do I express my ideas? How do I convey different ideas to you so that you can look at them and say, that idea makes sense and that idea doesn't make sense, without giving you like lengthy code. Okay. So let's recap what the grammar for arithmetic expressions was. So an expression can be a constant, which is just a number. An expression can be a variable or an identifier. Okay. Expression can be the sum of two expressions. Excuse me. Expression can be the subtraction of two expressions. It can be the product of two expressions using this mult constructor. It can be the division of two expressions, the log, exp, sine, cosine, and so on. Okay. Double maps to all double precision numbers in Scala. Identifiers maps to this regular expression. It maps to all strings that begins with letters, either small a to z or capital A to z, and can subsequently contain alphanumeric characters. Okay, but I'm going to drop that and say any string is an identifier for now. All right, so that's going to be my base language. And we already saw how to write this in Scala. You can take this grammar and write it as an inductive definition directly in Scala. No problems. Okay, and the question now is, how do we do values of expressions that you write? How do you evaluate it? For example, suppose I want to say evaluate log 1 plus 2 times y. Suppose I want to evaluate this log. Okay, in my language, this looks like this: log of plus of const of 1 multiply constant of 2 identifier y. Okay. And suppose I also said that y gets assigned to 1.2. Okay, so you need to tell me what y is, and on the side I tell you that y is 1.2. Okay, and that has a name that's called an environment. Okay, so an environment in an interpreter is something that carries around the names of all the identifiers that you know about, and they are all mapped to numbers. Because right now, numbers are the only type in our language, so everything is mapped to a number. Okay, that's the only thing we are working with right now. Eventually, you will get more and more and more things. You will get booleans soon, and then you will get functions, and you will get some representations of functions called closures, and you know, these things will grow. But right now, identifiers can only be numbers. That's the only type in our language. Okay, and I want to know how do we systematically go ahead and take care of evaluating something like this. Okay, and you can go bottom up and you can say, okay, I know that 2 is a constant, so that's just 2. I know that y is just 1.2. Okay, I know that if I multiply 2 and 1.2, I get 2.4. I know how to add 1 to 2.4, I get 3.4, and then I can do a log of 3.4 and I get my final answer. So there is a step-by-step way of doing it. Okay, so you know how to do it. Okay, but the question is, how do we do it on a computer? Okay, and this defines our basic function called eval. So we are going to define this function called eval. And what's eval? It's going to take in an expression which is going to be defined in this grammar. It's going to be of type expr, and it's going to take something called an environment. Environment is just going to be a mapping from names of identifiers to whatever values you have currently given them. So you can say, here is my environment. Whenever you see a y, it's a 1.2. Whenever you see a x, it's a 2.4. So you give the substitution. This identifier maps to this value. And who gave that to me? It's given. That's it. If you don't have the environment, then you are not going to be able to do it. Right? So environment is just a map. It's just a map from identifier names or strings to double precision numbers. Okay? You can think of it as a function. You get a name of a variable, and if you have it in the environment, you give a number. If you don't have it, then you raise an error and you say, how dare you, right? You haven't defined this, how dare you ask me for a value, right? Okay, is that good so far? And this is the function we want to define. We want to define eval. All right, and how do you want to define this? So this is basically there are two schools of thought on how to design this. Eval is going to be a recursive function. Why is that? Because remember, eval, for example, suppose your expression E is the plus, not pulse, plus. Suppose your expression E is the plus of two things, E1 and E2, under the environment. How do you eval the plus of two things? So if your expression E is that you're evaluating is made up of a plus operator on some sub-expression and some other sub-expression, and these two are complicated. You know, E1 can have log and sine and cosine inside it. E2 can have like a complicated series of operations inside it. How do you express the eval of plus of two things in terms of the two things inside it? So the way you would write it is to say this eval is the same as eval of E1 under the environment plus eval of E2 under the environment. So I get both the values and I just add them up. Okay, and this defines how do I evaluate the plus of two expressions under an environment is basically going to say evaluate each of the sub-expressions, take the values, whatever result you get, and add them up using the addition rule. Okay? What this gives us is an easy way of interpreting these things, but it also hides a lot of complexity. All right? So in programming languages, we express this thing using something called a semantic rule. So we express these things using something called a semantic rule. Okay, so what is a semantic rule? So a semantic rule looks like this. Let me write down an example of a semantic rule and let me talk about what it means. Question? It's kind of similar to distribution. So let me kind of talk about what it means. Okay, I'm going to go in like some inordinate boring level of detail into what this means, right? So let's write this as a semantic rule. So a semantic rule looks like this. So for example, here is a semantic rule that says eval plus E1, E2 under an environment env equals, and then you say on the top of so you draw a big line, so you draw this big line, and then on top you say eval. I'm not going to keep up these different colors, it's very hard for me to do that. E1 under environment gives rise to V1, so this V1 is a number for now, okay? We'll talk about what else it could be in a second. And then let's say eval E2 under the environment gives rise to V2. For now, let's assume V2 is a number. Again, there are going to be other cases where V2 might not be a number. Then this whole eval of plus E1, E2 is V1 plus V2. So the idea is this is called a semantic rule. So this is called a semantic rule. And you write this in a very strange notation, and this notation comes from logic. Okay? So the idea here is anything on the top is, you have to read it as if. Okay? Anything on the bottom, you read it as then. Oops, sorry. So the things on the top are called antecedents, and the thing on the bottom is called the consequence. So it says, if I could evaluate E1 under an environment and I get a number V1, and this is an and, I evaluate E2 under an environment and I get a number V2, then if I evaluate the constructor plus applied to E1, E2, then I get V1 plus V2. So to answer Julie's question, there is a difference between the plus here and the plus here. And we make a big deal out of this difference, and I'll tell you why. So this plus is the plus in my programming language syntax. So this is my programming language syntax plus. So what does it mean to be a programming language syntax plus? This is the plus that I write as a user, okay, in my programming language. This plus is the arithmetic operation of adding two numbers. Okay, so this is the arithmetic plus. So you could have called it add. So this plus, you could have called it anything you wanted. You could have called it add if you wished. You could have changed your grammar and you could have called it an add. You could have called it, I don't know, donkey. And maybe in your speak parlance, donkey of two expressions means you add the two expressions together. But the point is, this semantic rule is telling me that the programming language construct PLUS, those four letters in front of two expressions, will map to the arithmetic addition. Okay, it's kind of subtle. I mean, you start to get the point of this in a bit when I show you some very non-trivial things that you can express this way. But right now, the idea here is a programming language defines some syntax where you can write certain things. Whereas when you're interpreting this programming language, you're mapping those syntax, those things that you have written in your program to operations you know how to perform on a computer. So adding two numbers is an operation you know how to perform. This capital P, a small LUS, is a command to take an expression as having the addition of its two sub-expressions. And the semantic rule says that this plus should map to the sum of V1 and V2, the arithmetic sum, the function over numbers. Okay, not very surprising so far. Okay, so far? Let me give you another example of a rule. Okay, so let me give you another example of a rule. So this is one example of a semantic rule. So what would be a semantic rule for multiplication? So let me give you a semantic rule for multiplication. So you can say, let's do, so I'm not going to color things in different numbers. So eval of multiplication of two numbers E1, E2 under an environment env, what should that be? Well, you say, okay, on the top, if I evaluate E1 under that environment, I get a value V1. and V1 is a number. So this is R is a set of real numbers. So V1 is a number. And if I evaluate E2 under the environment, let's say I get V2 and V2 is a number. Then if I evaluate mult, then it should map to V1 star V2. So anything on the top is the antecedent of this rule. Okay, anything on the top is the antecedent, and these commas should be read as and. There is no way to put an or on the top. Everything is implicitly an and. So the way I read it is, if I evaluate an expression E1 under environment E and V, I get V1. And that V1 is a number. And you could ask me, what else could that V1 be, right? I haven't seen anything other than numbers. You will see in a second. It could be something else, right? And if I evaluate E2 under that environment and I get V2, and V2 is a number, then if I evaluate the mult of E1, E2 under that environment, it should evaluate to V1 times V2. Is that okay? So this is a specification. This is a specification. And I can have some strange, crazy specification. So let me give you an example of a semantic rule for multiplication. So as an example, here is a semantic rule for multiplication. Let's say eval E1 under an environment gives rise to V1. V1 is actually 0. Okay. Then eval E2, sorry, not E2, mult E1, E2 under that environment is also a 0. Okay, I could have also said V1 is a number, but you know, when I say V1 is 0, it already means V1 is a number. So I don't need to say redundantly that V1 is a number. It's a 0 for now. So here is a rule, right, for multiplication. Okay, and this rule does something very strange. It's a special case rule. And if I wrote a rule like this, then I have to go back and fix my rule up here and say, hey, by the way, this rule will only apply if V1 is not equal to 0. So I have to write somewhere up here when I have this rule that V1 is not equal to 0. Otherwise, these two rules will start clashing. They will both apply, and you want to know which one applies. So you want to make them mutually exclusive. Is that okay? Do you see where I'm coming from right now? So do programming languages have this kind of a rule? What do you think? So this is, you know, there is a reason, right? So what we are saying here is, if you evaluate E1 under an environment, the result is V1, but that V1 is already a 0, then I'm telling you, so what is missing here? What is missing here is any mention of E2, right? I'm not evaluating E2. I'm not like computing what E2 is. I am directly going in and saying the entire result of a multiplication is 0. So as an example, you could have 0 times a really long computation sequence here, which could have sine, cosine, like it could go on for like pages and pages and pages of computation. And what this rule is meant to say is, if you multiply that by a 0, the whole thing is a 0. So you don't need to do this long computation. You can just say the whole thing is 0. Do programming languages have this rule? What do you think? Question? Yes. So if I had this rule, right? So this is a different rule. Forget about this rule for now. Now in this case, I would have had to have a different rule, and I'd have said eval E1 under the environment is V1, and V1 is a number, and V1 is not 0. Then I have to say eval E2 under the environment is V2, and V2 is a number. So I say all these things. If all of these hold, then eval mult E1, E2 is under the environment E and V, under the environment E and V, so is V1 times V2. So this is how I would have written the rule. No. Okay, so the question is, do you need a specific rule for the case when E2 is 0? No. So right now what I have written is, I have written a rule for when E1 is 0. And then I have written, so then I have to write a rule for when E1 is not 0, because that's the other case, in which case I look at E2. So I'm always forced to look at things from left to right, but you could have looked at things from right to left. So you could have written a version of this rule where you looked at E2, if that is 0, the whole thing is 0. It depends on how you want to do it. But the point is, this is a bad rule, and I'm going to show you why semantics matters. Why is this a bad rule? Why do programming languages not have this rule? So the reason you wouldn't have a rule like this is exactly, try this in Scala. Try an expression like 0 times 100 divided by 0. What do you want the answer to be? Undefined, right? And most programming languages the answer will be undefined, not 0. So if you wrote a rule like this, then this rule is saying that this expression better be a 0. But that's not what programming languages do. Is that okay? Also, what programming languages also allow you to do, and we will build up to that later. Right now we don't have it. Programming languages also have side effects. So as an example, you could have written 0 times, okay, and then you could have opened up a complicated block, and you could have written some print statements, some input statements, some statements that command your rocket to thrusters, and then eventually, and put that all with a semicolon and eventually say 0. Okay, and these kinds of actions are called side effects. We'll talk about them later. But if the second computation, when you're doing E1 multiplied by E2, if E2 inside it had other things going on, right? Remember, you can sequentially, you can say statement A semicolon statement B semicolon statement C, then A and B are run, but the value that's returned is the value of the last statement. So the previous statements could have done some things like side effects, like transmit a packet over the network, send a file to a printer, send a command to the rocket thrusters to fire up and navigate to Jupiter, and then return the value 2. Okay? And if you put a 0 times in front of it in your old semantics, then all of those commands would never execute. In your new semantics, you want them to execute, right? So then the question is, programming language design is about making choices. I'm not saying it's wrong. I'm just saying choices have consequences. So you could make a choice saying 0 times anything is 0. So therefore, in my language, I'll build an optimization where I will first evaluate the first part of a multiplication. If that's already 0, I'll skip the entire multiplication over to the result. That's called short circuiting. But if you do short circuiting in multiplication, you skip over all these corner cases, right? And you can look at whether programming languages make this choice to short circuit multiplication, and you will see very few languages do. But it's a design choice. So these semantic rules I'm going to write, some aspects of this are very, very natural, right? If you say +2 expressions, you better add those expressions. Otherwise, no one wants to use your language. If you say multiply, then you better multiply. Okay, if you say divide, you better divide. But there are certain actions where you can make some choices. But if you make those choices, you'll have to deal with the consequences. So no programming language will short circuit. And let's do this in Scala and see what happens. So let's write 0 times 20 by 0. Okay, Scala complains. So Scala, when you give Scala multiplication, it does evaluate both sides of the multiplication. Is that okay? So semantic rules, you can write them in multiple ways. And in this course, you will see me write semantic rules all the time. Because that's an easy way to tell you how should you implement certain things in your language. Right? And then there comes the question of how do you implement these semantic rules, which I'll talk about next lecture. Today I'm just going to talk about the rules. Next lecture I'll present all the rules and I'll show you the implementation is just like writing a recursive function from the rules directly. There's nothing great going on there. Okay? So in our little language so far, we want to write a rule for division. What does the rule for division look like? Okay, so let's write the rule for division. So we can say, I want to know what does eval of the div of E1 and E2 under an environment What is it? So I want to write a rule like that. So then I say fine. If that's the case, let's eval E1 under the environment. And let's say the value is V1, and let's say V1 is a number. Let me say eval E2 under the environment is V2, and let's say V2 is also a number. Then I want to say that this is just V1 divided by V2. So I want to map this div to the operation of dividing two numbers. Reasonable? Except I get into a problem. And what's that problem? Division by 0. Okay. Now there are two types of languages on what happens when you divide by 0. Well, divide by 0, I mean, you can issue a divide by 0 to a processor. It will execute the instruction, but what will happen is, depending on whether you are dividing two integers and one of them is 0, whether it's integer division or floating point division, you get two different answers. In floating point division, you would get an answer called INF or minus INF, which is a special floating point number. Or if it is 0 divided by 0, you get a special floating point number called capital N-A-N, NaN, and that stands for not a number. Okay, the IEEE 756 standard tells you exactly what you should do when you divide a floating point number by a 0. Okay, and these are represented. So floating point arithmetic has that. Okay, but integer, what will happen is you would basically get a fault. Your processor will throw up a flag and say, I can't divide this, okay? And programming languages, it depends. They can silently just ignore it. Okay, so programming languages make multiple choices. One simple choice is silently ignore produce garbage. Which language makes that choice, you think? C, C++. Okay, those are nice languages that make that choice of, you can make them just silently ignore a division by 0, depends on which processor you're running, silently ignore a division by 0 and carry on. Okay, it depends on the operating system as well. Or you throw a flag, you throw an error. Okay, you throw an exception. That's the second choice, and that's the choice that Scala made. So if you look at what Scala has, so if you go back to Scala, you can see that division by 0 here in this example threw an exception. It threw a java.lang.arithmetic exception. It's a Java exception that got thrown where you're trying to divide by 0. So it's throwing an exception or throwing an error. There is a third choice you can make, and this is a choice made by certain languages like JavaScript, where dividing by 0 gives a new value called undefined. Okay, so it silently fails, but it doesn't return a number. It returns this value called undefined. It's not a number anymore. It's a new type of value. Is that okay? So in our semantics, we'll make that third choice. We will say dividing by 0 returns a value that we'll call the error value. Something went wrong value. It's not a number, but we'll call it error. Okay? So what is the rule for division then? So it turns out you can't write a single rule for division. You have to write two rules for division. So let me share that and show you what are the two rules you have to write for division. Okay, so what are the two rules? So the first rule is the OK rule for division. So what's the OK rule for division? So you say, if I'm going to divide by two numbers, if I'm going to eval div, so I'll just write this out again just for your convenience. Okay, and so you eval V1 or the first expression E1 under the environment. Let's say you get V1 and let's say that's a number, and let's say you eval E2 under the environment. Let's say you get V2 and let's say V2 is a number, and let's say V2, this is the most important part, you also say V2 is not 0. All of these are on the top. All of these are assumptions you have to make. So if all of these hold, that E1 when evaluated gives you a number, E2 when evaluated gives you a number, and that V2 number is not 0, then the whole thing is V1 by V2. This is safe. And this is called, let's call this rule division OK. So I will give my rules a name. So I'll call it division OK. Or I have to give a rule which produces an error. So in this rule, I would say eval E1 under environment gives me v1, which is a number. Eval e2 under an environment gives me v2, which is a number, but v2, let's say, is 0. In that case, evaluating the division of e1, e2 under that environment should give me a special value. So now I have to define a special value called error. Okay, so this is going to be a value. So now I get into trouble. Now arithmetic operations, if they succeed, produce a value which is a number. If they don't succeed, they produce a value which is an error. But that gets me into some kind of trouble. If I make this design choice and this is the design choice that JavaScript makes. This is the design choice that JavaScript makes. For example, okay, JavaScript doesn't call it error, it calls it undefined. So we will make that same choice. Now what is the problem? Can you imagine a problem now? So all your previous rules have to be modified. Why do they have to be modified? Because remember, if evaluating an expression can produce an error, then you have to say what happens if I try to add error to 15? So what happens if I have an expression like this in my program? So what happens if I have 100 divided by 0 plus 35? So remember, according to this rule here, and let's call this division error rule, 100 divided by 0 is error. So now I am in the unenviable position of adding some funny value called error to 35. So what should error plus 35 be? Error, right? So that makes sense, right? So you want error, once you reach an error, you want like sum of error to something be error, product of error to anything be error, right? So you want all of that, right? And you want error to get propagated properly, okay? And just like JavaScript does it, once you have error, then you have error, right? No complaints to anyone. It's like silently happening under the hood. Your computation completes without, but everything just becomes undefined.